Today, we're going to dig something up from the PET cemetery and attempt to resurrect it, a trashed amber Commodore PET. And the problem is, I don't know much about how monitors work with horizontal and vertical sync pulses and all that. So today, we're going to do three things. We're going to try to rescue the old PET itself, install a brand new IBM Amber monitor, and then figure out the video signals sufficiently so that I can connect one to the other. Come along for the ride and we'll figure it out together. Hey, I'm Dave. Welcome to my shop. I'm Dave Plummer, retired operating systems engineer from Microsoft going back to the MS-DOS and Windows 95 days. And back when I was 17, I dropped out of high school, jumped in my car, drove cross-country, and got a contract job writing 6502 assembly code for a Commodore 64 game company, Gremlin Graphics. By then, it was the mid-80s, and used PETs were already dirt cheap as schools were upgrading the PCs, so I bought this machine in a used computer shop way back then for about $25, and it's followed me around for nearly 35 years. This machine is unfortunately quite a mess, however, because it was one of the original 4K PETs. And to make sure it stayed that way, Commodore actually damaged the motherboard traces so as to prevent users from simply adding more RAM chips on their own. So instead, a friend used ultrafine wiring to rebuild the missing traces for me, then install the RAM chips, and it actually worked quite well for a long time, but now has multiple RAM failures, so the repair hasn't held up. Well, I guess it's been 35 years, so perhaps the repair is fine and the RAM is bad. It's actually hard to know. It also has a monitor problem that we've been unable to solve in that when the monitor enters its degauss cycle, it randomly locks up the motherboard. It must be backfeeding some kind of invalid signal that angers the motherboard, and it makes it very frustrating to use, at least for any length of time. Now, you might be thinking that there were no Amber PETs, and you'd be mostly correct. But a few weeks ago, I was surfing eBay, casually searching for a regular monitor for another project, when I stumbled across a 9-inch internal Amber monitor for the original IBM 5155 portable computer. It came straight from the cavernous halls of Computer Reset, an old computer warehouse of parts that was being slowly divested of its many treasures. If you've not heard of Computer Reset, I'll put a link to LGR's video about it in the description, and you should absolutely check it out next. Now, this was not some used eBay monitor sold as is and untested. It was actually brand new, still in the box, never opened, a 38-year-old IBM service part. Better yet, it was only $130 and the seller was even offering free returns if I couldn't get it to work. So how could I resist? Well, I couldn't. So even though I had no idea if I could make it work with a PET, I jumped on it immediately. There would be all kinds of problems to solve, but the most fundamental would be how to get a video signal out of the PET motherboard that I could use to drive an IBM monitor. You see, here's the thing. I don't know a lot about video signals. I'm a digital software guy, and that seems a lot like an analog hardware problem, so it's pretty far out of my lane. But I've been learning a lot of new stuff lately, so why not one more thing? Offhand, here's what I thought I knew about video signals. I know that the raster gun fills the screen in line by line, left to right, top to bottom. So there has to be some kind of vertical retrace signal that tells the gun when to reset and go back up to the top. Similarly, there must be a horizontal retrace signal that causes the gun to go back to the left and start the next scan line. Then you also need to know the gun intensity at any point in time, or the pixel brightness, and so that's the video signal itself. We're dealing in monochrome, so we can stop there, otherwise we'd have to add a color signal on top somehow. Now, if you're wondering if there's any kind of clock signal for controlling where the gun is on the line itself, there isn't, because the speed of the gun proceeding across and down the screen is defined by whatever video standard you're on, like NTSC. So the retrace signals synchronize the frames, but the drawing of the line across the screen proceeds at a known standard speed. The circuitry in the monitor draws at the same rate that the sender sends. So that's 3 signals: vertical, horizontal, and brightness. And it turns out that the PET video header on the motherboard has 3 signal lines. If we take a quick look at the monitor schematic, we can see exactly 3 video signals coming into it: video, vertical drive, and horizontal drive. It's very close to what I imagined. The connector itself has those 3 lines plus a ground for each and a blank pin to key the connector for a total of 7 pins. Let's take a look at that now. Pins 1, 4, and 7 are the signal grounds. I have no idea why they need 3 separate grounds, but I noticed that each signal is routed as a twisted pair with its own ground wire, so I'm going to guess that it's to avoid picking up noise. You see, if 2 wires run in parallel, they act as an antenna, but when they're twisted as a pair like that, it avoids having the cables ever truly run in parallel, so they don't pick up noise as a result. Pin number 2 is blocked off. It's just a blank to prevent you from getting the connector backwards or installing it on the wrong header. Since we're looking for what are effectively timing signals, I checked the master timing sheet for the PET, and sure enough, there are my 3 lines. Vertical drive on pin 3, horizontal drive on pin 5, and video signal on pin 7. So that's all well and good, and if the IBM monitor accepts them in that format, it should be smooth sailing. But you probably don't need a lot of foreshadowing to guess that it's not going to be that simple. So let's see what we can learn about the IBM monitor and what it expects for signals. I found the manual for the IBM 5155 display, which is a total of 3 pages. But right there on page 1 was the information I was after, display characteristics. And to my great surprise, it turns out that the monitor accepts a composite video signal. I was fully expecting a digital RGB signal with sync, but it wants nothing of the kind. I don't really get the how and why because the IBM 5155 Portable has a full monochrome MDA board in it, but it doesn't use the digital signal, which would essentially be just CGA with only one color. Instead, there's an internal composite video signal header on the adapter card itself. In a stock IBM 5155 Portable then, the internal monitor runs in composite mode and accepts its composite signal from that internal header on the display adapter over a simple 2-wire twisted pair, which is yellow and black. Now, all I knew about composite video is that it's what my Commodore 64 used. I assumed that my 3 signals, horizontal, vertical, and video, were somehow combined, but I had no idea how or by what process they were combined to make composite video, so it was off to Wikipedia to learn more. It actually wasn't basic enough, and it assumed I knew too much, so I had to surf around some more to some basic pages instead. And along the way I learned that composite video is also called CVBS for color, video, blanking, and sync. Now, we don't have the color portion, of course. So the waveform, it looks complex, and it is, but the parts we are interested in are the video and the sync. And at the end of the day, we can see that the waveform really amounts to our 3 signals combined. Thus, the composite video circuit in the monitor must take the combined signal and break out the horizontal, vertical, and video signals. All we need to do, it would seem, is to combine the 3 wires. Maybe I need a pull-down resistor and a diode to prevent backfeeding, but if I was lucky, it was going to be as simple as twisting all 3 wires together into one. Alas, it was not to be. I didn't even try it actually, since PETs are hard to find and the monitors are even more so. I couldn't afford to blow up either one with just a guess, so I did some homework on the actual format of the PET video signals and how to combine them. The first thing I found was a device that mixed the video signals from the PET motherboard into a composite video signal. Perfect, exactly what I wanted. Except like all things too good to be true, you can't get them like that no more. There's no add to cart button. But given that it had an IC on it, I now knew that the video combination process was clearly non-trivial. Or at least it was less trivial than just twisting all the wires together. But why? I found an ancient forum post from a user in Switzerland that explained why. Apparently, there are 2 major problems. The first is that the horizontal sync pulse on the PET is inverted. Rather than being a negative pulse, it's positive, so it needs to be inverted somehow. In fact, on newer PETs that have a CRT controller chip, there's actually a jumper that allows you to switch the sync pulses to the more conventional standard, but my PET is old school enough that it predates that support. The next problem is that the video signal itself is inverted. Although I might get a picture using the video signal as is with the syncs corrected, it would be black on amber instead of amber on black, and that would be completely wrong, so I had to fix that as well. I found the schematics to a couple of adapter circuits, and I decided to go with the one that made the most sense to me. Let's have a look at the one that I went with, and I'll walk you through it. And now remember, I'm a software guy, so it's a little like I'm a piano teacher who's teaching a class by staying 1 chapter ahead of her students. In other words, I barely know what I'm talking about. Feel free to point out errors and omissions in the comments, as I'd wager there will be a few and it might help the other viewers. What I did is I set up a breadboard with a 74 LSO2 chip and a power supply, and I rounded up the other little components that I would need. I actually keep very little electronics on hand, an assortment of resistors, capacitors, and a few chips and stuff like that, but I actually had everything I needed to build this circuit. The only exception was that I didn't have a cap quite that small, but I figured that wouldn't matter that much. I had a 0.1 microfarad, which seemed close enough. Famous last words. The 7402 chip has 14 pins, power, ground, and then it uses 12 of them to make 4 copies of a NOR gate. For example, pins 2 and 3 are the input and pin 1 is the output of the first gate. It's a logical gate that goes positive when neither input is high. If pin 2 or 3 or both are positive, then pin 1 will be negative. We'll be using that functionality to both combine and invert some signals in order to standardize the oddly inverted PET signals. I crimped pins onto those and kept as much twisted length as I could, and then inserted them into the ground rail of my breadboard. I started with the horizontal drive side since it's fairly simple. They feed it into both legs of the first NOR gate. That really just turns that gate into a simple inverter. If the horizontal sync pulse is high, it makes it low. If it comes in low, we make it high. Then, as you can see on the schematic, that corrected horizontal output goes to become one of the inputs to the next NOR gate. The other input to that gate is the vertical sync pulse. Unlike the horizontal, we don't need to invert it. So it appears this gate goes high whenever neither of the sync pulses is high. The vertical sync comes in on pin 3. There's a pull-down resistor to ensure that the signal actually drops to 0 when it's not active, and a capacitor whose purpose I'm not entirely sure of. My guess is that it acts as a battery of sorts on the sync line to maintain the black level, but I don't really know. If you do know, please drop me a hint in the comments. The vertical sync is combined with the horizontal sync via the second NOR gate, and the output of that is sent to the junction where everything is combined together. The video signal itself comes in on pin 7, and we use the third NOR gate as a simple inverter again, just like we did for the horizontal sync. We simply invert the video signal and then pass it on to be combined with the syncs. The combination of syncs and video is done with a set of resistors and caps that are above my pay grade in terms of the actual values selected. I can see there's a voltage divider surrounding the output of the video circuit, but as to why and what values, I'd appreciate your explanation to me in the comments if you know. In fact, any other light that you can shed on this circuit would also be useful in the comments. What cool aspects of it did I overlook? Let me know. My knowledge of these analog display circuits is obviously a little cursory, so I'd appreciate it if you can fill in the gaps, and perhaps I can return the favor in a future episode in an area where I know more. The composite output is therefore a single wire plus ground. Once I had the circuit built, I mocked everything up. Rather than risk my precious amber monitor though, I connected the output to a composite HDMI converter and then ran that output to a small HDMI field monitor. I powered up the monitor and the display circuit and the composite box and crossed my fingers, but it came up blank. No signal at all actually, according to the little converter box. I checked and rechecked my breadboard circuit. When I'd looked for a long time without spotting anything, I had a local electrical engineering student look at it and then sent a photo of the schematic and my board off to a pro, but no one could see anything wrong. And then I figured it out. I had forgotten to turn the PET on itself. You see, all 4 power supplies have to be up and running before it'll work, and as soon as I powered up the PET, I had a signal at the monitor. Unfortunately, the signal was scrambled sideways, and though I had high hopes based on the fact that you could see the image of what appeared to be the Commodore BASIC in the background. I was trying to spot boobs when you're watching HBO that's been scrambled in the 1980s. You might remember that earlier I mentioned that I didn't have the right capacitor, so I was hoping that was the problem. I ordered an assortment off eBay and went to bed for the night, and in the morning decided to build a new copy of the circuit on prototyping board. I did so but got the exact same result. That told me that it most likely was that capacitor, and I couldn't wait any longer, so I hopped in the car and drove to Vetco Electronics, a local electronics superstore. We're super fortunate to have a place like Vetco nearby here in the Seattle area, and it's the kind of electronics store that Radio Shack wanted to be when it grew up. For example, they don't keep their capacitors in a drawer. They keep them in 2 long aisles. I quickly found the 2200 picofarad cap, not only in the ceramic style that I needed, but also in a dozen other styles and voltages as well. With the correct cap installed in both my breadboard and the prototype board, I powered everything back up, and sure enough, other than a little electrical noise, the Commodore banner appeared on my field monitor. Success. Now to connect it all up on the real amber display. Now, when actually installed in the original IBM 5155, the amber monitor actually taps an unregulated supply off the mains power transformer. Apparently this provides some benefits such as shutting the entire supply down in the event of any fault, but it wasn't clear to me exactly what kind of power it was getting. So a more knowledgeable friend from Microsoft named David Oliver checked into it for me and concluded that I would be able to get away with a standard 12-volt DC supply, so I connected the monitor to my benchtop supply for now and dialed in 12 volts. Sure enough, up came my PET directory listing on the IBM monitor. It was still full of electrical noise and the horizontal sync was a little off, but it was working. By the way, anytime I show you a recording of the monitor taken on my phone like this, you're going to see a dark section roll through the picture. That's because the refresh rates don't match between the camera and the monitor, but you don't see it that way in person with the naked eye, just on the camera. Next came a number of construction steps in mounting the monitor to the PET case. I had to remove the top shielding in order to get it in and out of the factory monitor housing, but once I did, it fit reasonably well. To my surprise and dismay, however, the 4 mounting ears for the IBM 9-inch monitor are not in the same place as with the Commodore monitor. You'd think that such things would be reasonably standardized, but apparently not. Instead, I bent the mounting ears out of the way and then fabbed my own retention system that used the factory bolt holes to retain the IBM monitor via large washers that hold it forward against the bezel. I'd need a 5V and 12V supply, and though I could steal power from the mainboard, I wasn't comfortable in doing so, even though I suppose it was designed to support the extra demand of a monitor right from the beginning. I decided to add a compact but powerful Meanwell supply that offered both voltages. I'd use the 5V to run my signal converter board and the 12V to run the monitor. I initially mounted the power supply up in the monitor housing, thinking I'd be okay because both had RF shielding. However, the magnetic field of the power supply curved the picture slightly, and so I had to move the power supply back down into the main case. I wired it into the existing switch and fuse assembly so that it is only powered on when the PET is also switched on. At idle, the monitor pulls 0.8 amps. I'd love to hear your opinion on whether I could get away with attaching it to the output of the 7812 regulator that's already there. They can support 1.5 amps, but I'm not sure how much load is already on it. Let me know what you think in the comments. The picture was bright and crisp, and as you can imagine, a monitor that's never been powered on in its life before would be, but it wasn't quite centered. I searched and searched in vain for a horizontal position adjustment on the CRT board, but there just wasn't one. So instead, I used the magnetic ring adjustments on the neck of the board to move the picture over. They're a lot like the convergence rings in a color set, but of course there's only a single pair. They seem to adjust the deflection of the beam so that you can change the picture's ultimate position on the screen. Now that I had a working amber display, it was time to tackle the mainboard's problems. And the reality is that I just don't trust this board beyond the original row of chips. The ones that were on the spots destroyed by the factory are just never going to be reliable in my mind, so this mainboard is limited to 16K. I wanted a 32K PET with at least basic 4 and ideally a PET SD Plus to load images from, and I decided that the best solution would be a ROMulator. The ROMulator sits in between the 6502 and its original slot, and it intercepts the address and data lines. It can either refer them on to the original lines on the mainboard or route them instead to internal ROM images and internal RAM. That allows you to upgrade or replace all of the RAM in your system at once, as well as giving you numerous choices of ROM images to boot with. While I awaited the ROMulator, I managed to get a hold of a loaner MINIPET replacement board, so I decided to put it through its paces by making it my new mainboard, at least for now. The first thing I saw when I looked at the MINIPET board was a composite video output. It's almost kind of cheating, but it would mean that I wouldn't need my signal converter logic while using the MINIPET. I set it aside and went about removing the monitor as I wanted to redo my physical mounting and wire in a longer signal cable. I took the entire monitor housing off as that would allow me to work on it as an assembly, and it makes the base a little easier to work on as well. I cleaned the base and went about test fitting the MINIPET board. It uses the rearmost 2 factory mounting screws, and then, because the board is so much shorter than the original, they supply adhesive back standoffs to secure it up front. There's only one really annoying flaw with this board, and that's that the composite video connector comes out in dead ends up against the steel wall of the PET's case. If it pointed up, it'd be more useful, but I decided to forego the RCA connection entirely and wire in my own. I soldered in black and yellow wires to match the factory ones, and then added a 2-pin connector between the mainboard and the monitor to allow for the CRT's removal. I found the PET easier to work on when flipped onto its side for some operations, such as installing the mainboard or the monitor housing. Once the mainboard was secure, I buttoned up the remaining items like securing the transformer and then powered it up. It booted immediately to a beautiful, crisp and bright display of MINIPET Basic 4.1. The MINIPET can quickly and easily be reconfigured via dip switches, so naturally, after confirming that Space Invaders work properly, I set the internal SD drive to be drive 9 so that my trusty D9090 hard drive could remain as factory drive 8. Next, I tried 80 column mode and it worked perfectly as well. I don't have a great deal of use for 80 column mode on the tiny 9-inch display, but it's great to know that it works. I was highly impressed with just how flexible the MINIPET board was and what a complete replacement it seems to be. I tested the IEEE support with both my PET SD Plus and the real Commodore hard drive, and it seems quite compatible. The only significant difference from a stock PET that I noticed is that you can reset the machine a little too quickly and it won't boot. You have to leave it off for like 5 seconds before turning it on, whereas the real PET had a 555 timer circuit to ensure that reset was held low or high, active enough to complete the reset. While I heartily recommend this piece of hardware, I just can't recommend the company that I got the board from, as I had a rather poor experience with their customer service. I'm not a big fan of YouTube channels flexing on vendors they dislike, so I'm not going to do that, but I won't actively promote them either. The reality is that I think there are more PET motherboards in the world than there are working keyboards and monitors, so the problem isn't finding a good one. The last one I bought off eBay had obviously been on fire at some point and was sold as is. That kind of nonsense gets old in a hurry, so this board is at least refreshingly brand new and reliable. I appreciate you joining me out here in the shop today. If you're not already subscribed to my channel, I'd be honored if you'd consider subscribing, and if you found this episode some combination of entertaining and informative, please give it a like. If you have any interest in matters related to autism, Asperger's, or ASD, please check out my book on Amazon, Secrets of the Autistic Millionaire. It's got nothing to do with money and everything to do with living a successful life on the spectrum. It's everything I know now that I wish I'd known back then. Remember, I'm just in this for the subs and likes, so please be sure to leave me one of each before you go today. In the meantime and in between time, hope to see you next time, right here in Dave's Garage.